Picture this: 500 million years after the Big Bang, a black hole 100 times the mass of the Sun is already devouring gas at a rate that would power a million suns. This isn't just massive, it's a cosmic speed bump in the universe's infancy, defying models that say such giants take billions of years to form. How did this monster, heavier than entire star clusters, collapse into existence so soon? Astronomers stumbled upon its glow in the faint afterglow of the early universe, a signal so extreme it rewrote the rules. This isn't just a black hole, it's a star-sized beast forged in the universe's cradle, challenging everything we thought about how galaxies and their monsters grow. What secrets does it hold about the universe's earliest days? And why did it shine so brightly, so quickly? In a groundbreaking discovery, astronomers have identified a black hole in the early universe, a finding that challenges existing theories about how these cosmic giants form. This black hole, observed in a region of space dating back just a few 100 million years after the Big Bang, is significant because it suggests that some black holes may have formed not through the collapse of massive stars, but through a different process entirely. The discovery has sparked new questions about the evolution of galaxies and the role black holes play in shaping the universe. Let me explain what this means and how scientists arrived at this conclusion. Black holes are among the most mysterious objects in the cosmos, regions of space where gravity is so intense that not even light can escape. Traditionally, scientists believe that most black holes form when massive stars, those with tens or hundreds of times the Sun's mass, reach the end of their lives. These stars burn through their fuel rapidly, collapsing under their own gravity to form either neutron stars or black holes. However, the earliest stars in the universe were even more massive, and their lifetimes were extremely short. If these stars collapsed into black holes, they would have left behind remnants that could be detected today. Yet, until now, the earliest known black holes were much larger, suggesting they might have formed through a different mechanism. The discovery in question changes that narrative. The black hole in question is relatively small, about 10 times the mass of the Sun, yet it was found in the early universe, a time when the universe was only a few 100 million years old. This is significant because, according to current models, such a black hole should not have existed so early. If it formed from a collapsing star, it would have required a star with an unusually high mass, which would have burned out in just a few million years. But the black hole's existence suggests that it formed in a way that defies traditional expectations. Scientists are now considering alternative explanations, such as the possibility that this black hole formed from the direct collapse of a gas cloud rather than from a star. Direct collapse occurs when a massive gas cloud collapses under its own gravity without forming a star first, leading to the immediate formation of a black hole. This process could explain how such a massive black hole could exist so early in the universe's history. But how did astronomers detect this black hole? The answer lies in a combination of observational techniques and advanced technology. The black hole itself does not emit light, but its presence can be inferred through its effects on nearby matter. In this case, scientists observed a system where the black hole is part of a binary star system. One star orbits the black hole, and as the star's material is pulled into the black hole's intense gravitational field, it heats up and emits X-rays. These X-rays were detected by space-based observatories, allowing scientists to pinpoint the black hole's location. The system's age, determined by the light it emitted and the distance it traveled across space, places it in the early universe. This is the first time such a small black hole has been observed in such an early epoch, making it a unique find. The implications of this discovery are profound. For decades, scientists have debated how the first black holes formed. Some theories suggested that the earliest black holes were massive, formed through direct collapse, while others proposed that they were smaller and grew over time by accreting gas and merging with other black holes. This discovery adds a new layer to that debate. The presence of a small black hole in the early universe suggests that there may have been multiple pathways for black hole formation. It also raises questions about the role of these early black holes in the evolution of galaxies. Black holes are known to influence their host galaxies through feedback mechanisms, such as jets of high-energy particles and radiation that can regulate star formation. If small black holes existed in the early universe, they may have played a more significant role in shaping the first galaxies than previously thought. Moreover, this discovery challenges the timeline of stellar evolution. The earliest stars in the universe were thought to be extremely massive, with masses ranging from hundreds to thousands of times that of the Sun. These stars would have burned through their fuel in just a few million years, leaving behind black holes that could have been the seeds for the supermassive black holes observed in the centers of galaxies today. However, the existence of a small black hole in the early universe suggests that the process of black hole formation may have been more complex. It could mean that some black holes formed from stars, while others formed through direct collapse, leading to a diverse population of black holes in the early universe. This diversity would have influenced how galaxies formed and evolved, as different types of black holes would have interacted with their environments in different ways. Another intriguing aspect of this discovery is its potential impact on our understanding of dark matter. While dark matter remains one of the greatest mysteries in astrophysics, some theories suggest that it could be composed of weakly interacting massive particles, WIMPs, or other exotic particles. However, the presence of a small black hole in the early universe does not directly relate to dark matter. Instead, it highlights the need for more precise models of how black holes form and evolve. The discovery also underscores the importance of continued observations with next-generation telescopes, which can peer deeper into the universe and detect fainter signals from the early cosmos. Instruments like the James Webb Space Telescope and the upcoming Lynx X-ray Observatory could provide even more insights into the formation and growth of black holes in the early universe. It's worth noting that this discovery is not an isolated event. In recent years, astronomers have found other black holes in the early universe, some of which are even more massive. These findings collectively suggest that the formation of black holes may have been more varied and dynamic than previously thought. The early universe was a chaotic and energetic place, with gas clouds collapsing under their own gravity, stars forming and dying in rapid succession, and black holes emerging as the remnants of these processes. The discovery of this particular black hole adds another piece to this complex puzzle, offering new perspectives on how the universe evolved from its infancy to its current state. For scientists, this discovery represents both a breakthrough and a challenge. It confirms that our understanding of black hole formation is incomplete and that there is still much to learn about the early universe. The fact that a small black hole could exist so early in cosmic history suggests that the processes that govern black hole formation are more nuanced than previously believed. It also highlights the importance of interdisciplinary research, as understanding black holes requires knowledge of stellar evolution, gravitational physics, and observational astronomy. By combining these fields, scientists can develop more accurate models of how black holes form, grow, and interact with their surroundings. In conclusion, the discovery of a black hole in the early universe is a testament to the power of modern astronomy and the ingenuity of scientists who continue to push the boundaries of our knowledge. This black hole, with its relatively small mass and early formation, challenges existing theories and opens new avenues for research. It reminds us that the universe is full of surprises, and that our understanding of it is always evolving. As we continue to explore the cosmos, discoveries like this will undoubtedly shape the future of astrophysics, offering new insights into the origins of black holes, the formation of galaxies, and the fundamental nature of the universe itself. Let's take a closer look at how scientists uncovered this astonishing discovery. The journey to uncover a black hole star in the early universe began with a combination of cutting-edge technology and decades of theoretical groundwork. At the heart of this breakthrough was the James Webb Space Telescope, a marvel of modern engineering designed to peer into the cosmos with unprecedented clarity. Launched in 2021, Webb's infrared vision allows it to detect light from the earliest galaxies, which has been stretched and dimmed by the universe's expansion. But even with Webb's capabilities, the task was far from simple. The object in question existed over 13 billion light-years away, meaning its light has traveled for nearly the entire age of the universe to reach us. To detect such a faint signal, astronomers had to rely on a suite of instruments, each contributing a unique piece of the puzzle. Among them was the Atacama Large Millimeter/Submillimeter Array, or ALMA, a network of radio telescopes in Chile that can capture subtle emissions from distant celestial objects. Together, these tools formed a powerful observational network, capable of peering into the universe's infancy. But the process didn't stop at data collection. Scientists had to navigate a labyrinth of challenges, from distinguishing the faint glow of a black hole from the background light of the cosmos to verifying their findings through multiple methods. The discovery itself was rooted in a phenomenon known as an accretion disk, a swirling mass of gas and dust that spirals around a black hole, heating up to extreme temperatures and emitting light. This light, though faint, is a telltale sign of a black hole's presence. However, detecting such a signal in the early universe required more than just advanced telescopes. It demanded a deep understanding of how these objects form and evolve. Theories suggested that black holes in the early universe could have formed from the collapse of massive stars, but the existence of a black hole star, essentially a black hole that has begun to accrete matter, challenged existing models. To confirm this, astronomers turned to a multi-wavelength approach, combining data from optical, infrared, and radio observations. Each wavelength revealed different aspects of the object. Optical light might show the glow of nearby stars, infrared could trace the heat of the accretion disk, and radio waves might detect the faint emissions from the surrounding gas. By cross-referencing these signals, scientists could build a comprehensive picture of the object's properties. Yet, the process was far from straightforward. The early universe is a chaotic era, filled with dense clouds of gas and intense radiation. Any signal from a black hole star would have been obscured by this environment, requiring precise calibration of instruments and meticulous analysis of the data. Astronomers also had to account for the universe's expansion, which stretches the wavelength of light over time. This redshift effect meant that the light from the object appeared in a different part of the electromagnetic spectrum than it originally emitted, complicating efforts to interpret the data. To overcome these hurdles, teams of researchers worked in tandem, using sophisticated algorithms to filter out noise and isolate the faint signals they sought. The timeline of this discovery was equally intricate. The initial observations began with deep space surveys conducted by the James Webb Space Telescope, which scanned vast regions of the cosmos for distant light sources. These surveys, which took months to complete, generated terabytes of data, each pixel representing a potential clue. From this data, astronomers identified a faint but distinct signal that warranted further investigation. Follow-up observations using ALMA and other radio telescopes confirmed the presence of a massive accretion disk, while additional data from the Hubble Space Telescope provided critical context about the surrounding environment. The collaboration between these observatories was essential, as each contributed a unique perspective to the puzzle. For instance, while Webb's infrared capabilities allowed researchers to detect the heat of the accretion disk, ALMA's radio sensitivity revealed the presence of cold gas surrounding the black hole, offering insights into its formation. This interplay of data not only confirmed the existence of the object but also provided clues about its history. The discovery itself was a testament to the power of modern astronomy, but it also raised profound questions about the early universe. How could a black hole star form so quickly after the Big Bang? Traditional models suggested that black holes needed billions of years to grow through the accretion of gas and mergers, but this object appeared to have formed in a fraction of that time. This discrepancy hinted at new possibilities, such as the existence of primordial black holes or alternative formation mechanisms. To explore these ideas, scientists had to delve deeper into the data, analyzing the object's properties in detail. They measured its mass, luminosity, and the rate at which it was accreting material, comparing these findings to existing theories. The results were striking. The black hole star was not only massive but also unusually bright, suggesting it had been actively feeding on surrounding gas for a significant period. This brightness, however, posed another mystery. How could such a massive object have formed so quickly without disrupting its environment? The answer may lie in the unique conditions of the early universe, where dense gas clouds and intense radiation could have accelerated the formation process. Yet, these theories remain speculative, and further observations are needed to confirm them. The significance of this discovery extends beyond the object itself. It challenges our understanding of black hole evolution and the role these enigmatic entities play in shaping the universe. Black holes are not just cosmic curiosities, they are integral to the life cycles of galaxies, influencing star formation and the distribution of matter. By studying objects like this black hole star, astronomers can gain insights into how these processes unfolded in the early universe. Moreover, the discovery highlights the importance of technological advancements in astronomy. Instruments like the James Webb Space Telescope and ALMA are not just tools for observation, they are gateways to understanding the universe's past. Each new discovery builds on the foundation laid by previous missions, creating a cumulative body of knowledge that reshapes our view of the cosmos. As scientists continue to analyze the data from this discovery, they are also planning future missions to explore similar objects. Upcoming observatories, such as the Square Kilometre Array, promise to provide even greater resolution, enabling researchers to probe deeper into the universe's infancy. The journey to uncover this black hole star was a complex and collaborative effort, but it exemplifies the spirit of scientific inquiry. By combining cutting-edge technology, theoretical insight, and meticulous analysis, astronomers have opened a new chapter in our understanding of the universe. This discovery is not just a milestone in its own right, it is a stepping stone toward unraveling the mysteries of the cosmos, one light year at a time. In the vast tapestry of the cosmos, black holes have always been enigmatic giants, regions of spacetime where gravity is so intense that not even light can escape. But the discovery of a black hole star in the early universe has thrown a wrench into our understanding of how these cosmic behemoths form. To grasp why this finding is so significant, we need to rewind to the birth of the universe itself and explore the delicate dance of matter and energy that shaped the first stars and, ultimately, the black holes they birthed. Stars are the universe's factories, forging elements from hydrogen and helium into the building blocks of planets and life. But when a star exhausts its nuclear fuel, its fate depends on its mass. The most massive stars, those hundreds of times the Sun's size, end their lives in spectacular supernova explosions, collapsing under their own gravity to form black holes. This process, however, requires time, billions of years for the universe to cool and for stars to form, evolve, and die. Yet, the discovery of a black hole in the early universe suggests that these cosmic monsters might have emerged far earlier than previously thought, challenging the timeline we've long accepted. The early universe was a harsh and chaotic place. Just 100 million years after the Big Bang, the first stars began to form from primordial gas clouds. These stars, known as population 3 stars, were unlike anything we see today. They were massive, perhaps hundreds of times the Sun's mass, and burned through their fuel in a blink of cosmic time. When these stars died, they should have left behind black holes, stellar remnants with masses ranging from a few to dozens of solar masses. But here's the catch: the conditions in the early universe were so extreme that these black holes might have formed in ways we haven't yet fully understood. Perhaps they didn't require the same slow, steady collapse of a massive star. Maybe they formed through different mechanisms, such as direct collapse from gas clouds or mergers of smaller black holes. This discovery adds a new layer to the story. If a black hole formed in the early universe, it could have acted as a gravitational seed for the first galaxies. Black holes, even small ones, exert a powerful influence on their surroundings. Their immense gravity can pull in gas and dust, triggering the formation of stars and shaping the structure of galaxies. In the early universe, where matter was still clumping together to form the first galaxies, such a black hole could have played a pivotal role. It might have acted as a catalyst, helping to concentrate gas and dark matter into the nascent galaxies we see today. This connection between black holes and galaxy formation is a cornerstone of modern cosmology, and finding evidence of this process in action so early in the universe is a game-changer. But why does this matter? Well, the universe is a dynamic place, and every discovery adds a piece to the puzzle of its evolution. If black holes formed earlier than we thought, it could mean that the universe's timeline is more compressed than previously believed. It might also suggest that the processes governing star and black hole formation are more varied than we've accounted for. For instance, the standard model of black hole formation relies on the collapse of massive stars, but if we find evidence of black holes forming through other means, it could force us to rethink the entire life cycle of these objects. This could have ripple effects across astrophysics, from the study of gravitational waves to the search for dark matter. Another angle to consider is the role of these early black holes in the cosmic web. The universe is a vast network of filaments of dark matter, with galaxies forming at the intersections. If a black hole formed in the early universe, it might have influenced the distribution of matter in ways we haven't yet modeled. For example, the energy released by a black hole's accretion disk, where gas spirals into the black hole, heating up and emitting radiation, could have affected the surrounding gas, altering its temperature and density. These changes might have influenced the formation of subsequent stars and galaxies, creating a feedback loop that shaped the universe's structure. Moreover, the discovery of such a black hole raises questions about the nature of dark matter itself. While dark matter remains one of the greatest mysteries in astrophysics, some theories suggest that primordial black holes formed in the early universe, could be a form of dark matter. If this black hole is indeed a primordial black hole, it could provide a tangible link between the visible universe and the invisible dark matter that makes up most of the cosmos. This connection is not just theoretical, it could help us refine our models of dark matter and its role in the universe's expansion. The implications extend beyond the immediate. Understanding how black holes form and evolve is crucial for predicting their behavior in the present day. Supermassive black holes, which reside at the centers of galaxies, are thought to have grown through mergers and accretion over billions of years. But if smaller black holes formed in the early universe, they might have provided the seeds for these supermassive giants. This means that the history of black holes is intertwined with the history of galaxies, and studying one can shed light on the other. The discovery of this early black hole could help us piece together this complex puzzle, offering insights into how galaxies and black holes co-evolved. However, the significance of this discovery isn't just about the black hole itself. It's about the broader picture of the universe's development. The early universe was a time of rapid change, with matter clumping together, stars forming, and the first galaxies taking shape. Finding evidence of a black hole in this era challenges our assumptions about the timeline of these events. It suggests that the processes we observe today might have roots in a much earlier, more chaotic period. This could mean that the universe's history is more interconnected than we've previously thought, with each stage influencing the next in ways we're only beginning to understand. In the end, this discovery is a reminder of how much we still have to learn about the cosmos. The universe is a vast, complex system, and every new finding adds a new dimension to our understanding. By studying the early universe and the objects that shaped it, we can gain insights into the fundamental forces that govern the cosmos. The black hole star in the early universe isn't just a curiosity, it's a key to unlocking the secrets of the universe's past, present, and future. As we continue to explore the cosmos, each discovery brings us closer to answering the timeless question, how did the universe come to be? For decades, astronomers have gazed at the cosmos, piecing together the story of how the universe evolved from its earliest moments. At the heart of this story lies a fundamental question: how did the first stars and black holes form? For years, scientists believed that massive stars, those with tens or even hundreds of times the Sun's mass, were the precursors to black holes. These stars, they thought, lived fast and died young, collapsing under their own gravity to form black holes within a few million years. But the discovery of a black hole star in the early universe challenges this long-held assumption, forcing scientists to reconsider the origins of these enigmatic objects. To understand how we arrived at this revelation, we must first journey through the history of astrophysics, from the first hints of black holes to the groundbreaking observations that reshaped our understanding of the cosmos. The story begins in the mid-20th century, when astronomers first began to suspect that some celestial objects might be black holes. In the 1960s, radio telescopes detected mysterious sources of energy, quasars, that seemed to defy explanation. These objects, located in the distant universe, emitted vast amounts of light, far exceeding what could be produced by ordinary stars. It wasn't until the 1970s that scientists proposed a radical idea: these quasars might be powered by supermassive black holes at the centers of young galaxies. This theory, though controversial at the time, laid the groundwork for understanding black holes as cosmic engines of energy. But black holes themselves were not directly observed until the 1970s and 1980s. The first confirmed black hole candidate, Cygnus X1, was identified in the 1970s. This object, located in our own galaxy, exhibited the telltale signs of a black hole. It pulled material from a companion star, heating it to extreme temperatures and emitting X-rays. This discovery confirmed that black holes could exist in the universe, even if they remained invisible. Over the next few decades, astronomers refined their methods for detecting black holes, using X-ray observatories like the Einstein and Chandra satellites to study these elusive objects in greater detail. As our understanding of black holes grew, so did our curiosity about their origins. By the 1990s, scientists had begun to explore how these massive objects formed. The prevailing theory was that black holes formed from the collapse of massive stars, which themselves had lifetimes measured in millions of years. These stars, known as population 3 stars, were thought to be the first stars to form in the universe, shortly after the Big Bang. However, these stars were extremely massive, and their short lifetimes meant they would have collapsed into black holes quickly, leaving little time for them to influence the early universe. Yet, this model struggled to explain the presence of supermassive black holes in the centers of galaxies billions of years ago. How could such massive objects form so rapidly? The 2000s brought a new wave of discoveries that deepened this mystery. Observations of distant galaxies revealed that supermassive black holes existed in the early universe, just a few 100 million years after the Big Bang. These findings raised a critical question: if black holes formed from massive stars, how could they grow to such enormous sizes so quickly? The answer lay in the study of star formation itself. Astronomers realized that the early universe was a vastly different place than the one we see today. It was denser, filled with primordial gas, and free of the heavy elements that now shape star formation. These conditions might have allowed for the formation of stars with masses far exceeding those of modern stars, potentially leading to the rapid creation of black holes. The development of powerful telescopes in the 2010s and 2020s brought new tools to this quest. The James Webb Space Telescope, launched in 2021, has revolutionized our ability to observe the early universe. Its infrared capabilities allow it to peer through the cosmic fog that obscures the distant past, revealing galaxies and objects that were previously invisible. These observations have confirmed that the early universe was a dynamic place, with galaxies forming and evolving at an incredible rate. But even with these advancements, the question of black hole formation remained elusive. How could such massive objects have formed so quickly? And what role did the first stars play in this process? The breakthrough came as scientists began to realize that the traditional model of black hole formation might not be the whole story. In the 2010s, theoretical models suggested that black holes could form not only from the collapse of massive stars but also through a process called direct collapse. This theory proposed that in the early universe, dense gas clouds could collapse directly into black holes without first forming stars. These primordial black holes, if they existed, could have grown rapidly by accreting surrounding material, eventually becoming the supermassive black holes observed in the centers of galaxies. However, this theory lacked direct observational evidence until recently. The discovery of a black hole star in the early universe marks a pivotal moment in this evolving narrative. This object, which appears to be both a star and a black hole, challenges our understanding of how these two entities interact. If such an object exists, it suggests that the boundary between stars and black holes may be more fluid than previously thought. It also raises new questions about the conditions in the early universe. Could this object have formed in a way that defies our current models of stellar evolution? And what does its existence tell us about the processes that shaped the first galaxies? To fully appreciate the significance of this discovery, we must look back at the decades of research that led to it. From the first hints of black holes in the 1960s to the development of advanced telescopes in the 21st century, each step has brought us closer to understanding the universe's most extreme objects. The journey has been one of curiosity and persistence, driven by the desire to uncover the secrets of the cosmos. And now, as astronomers peer deeper into the universe than ever before, they are beginning to see a picture that challenges everything we thought we knew about the origins of black holes and the stars that gave rise to them. This discovery challenges our current understanding of how black holes form and evolve. For decades, astronomers have believed that black holes grow gradually, starting from the collapse of massive stars and then accreting matter over millions of years. But this black hole star, observed in the early universe, defies that timeline. It suggests that some black holes may have formed in a completely different way, perhaps through a process that allowed them to grow massive in a fraction of the time. Yet, the exact mechanism remains elusive, sparking intense debate among scientists. How could such a massive object exist so soon after the Big Bang? And what does this mean for our understanding of cosmic evolution? These questions are at the heart of the mystery, and they point to a deeper puzzle: the role of dark matter in shaping the universe's earliest structures. While dark matter itself remains invisible, its gravitational influence is thought to have played a critical role in galaxy formation. Could it have also influenced the formation of these early black holes? Some researchers propose that dark matter halos might have provided the necessary conditions for black holes to form directly from collapsing gas clouds, bypassing the traditional stellar evolution pathway. But without direct evidence, these ideas remain speculative. The challenge lies in reconciling this discovery with existing models while accounting for the vast uncertainties that still surround the early universe. For instance, the methods used to detect this black hole rely on observing its gravitational effects or the light it emits, but these signals are often faint and difficult to distinguish from other cosmic phenomena. The team behind the discovery has emphasized that their findings are based on meticulous analysis of data from advanced telescopes, yet the interpretation of such data is inherently complex. Even if the black hole's existence is confirmed, its implications for the broader cosmic timeline are still unclear. One possibility is that this black hole represents an exception to the norm, a rare case where alternative formation mechanisms took hold. However, if such cases are more common than previously thought, it could force a complete re-evaluation of how black holes and galaxies co-evolved. Another layer of uncertainty lies in the relationship between black holes and their host galaxies. In the modern universe, supermassive black holes are often found at the centers of galaxies, and their growth is thought to be linked to the galaxy's evolution. But this black hole star, observed in the early universe, may have existed in a different context. Did it influence the formation of its host galaxy, or was it a byproduct of some other process? These questions highlight the interplay between cosmic structures and the forces that shape them. The discovery also raises intriguing questions about the role of feedback mechanisms in the early universe. Black holes, when they accrete matter, release enormous amounts of energy in the form of radiation and jets. This energy can heat up surrounding gas, suppressing star formation and altering the dynamics of galaxies. If this black hole star existed in the early universe, its activity could have had a profound impact on its environment. Yet, the extent of this influence remains speculative. Scientists are now working to model these scenarios, but the lack of direct observational data makes it difficult to draw definitive conclusions. Moreover, the discovery challenges the assumption that all black holes follow a similar evolutionary path. While most black holes are thought to form from the remnants of massive stars, this black hole star suggests that there may be multiple pathways to their formation. Some researchers have even proposed that the earliest black holes could have formed directly from the collapse of primordial gas clouds, a process known as direct collapse. This theory, however, requires specific conditions that are still not fully understood. For example, the presence of certain types of gas or the absence of cooling mechanisms could have allowed such massive structures to form rapidly. But without clear evidence, these ideas remain part of an ongoing scientific conversation. The implications of this discovery extend beyond black holes themselves. If early black holes formed in ways that differ from their modern counterparts, it could mean that the universe's structure evolved in more complex ways than previously imagined. Galaxies, for instance, might have formed under different conditions, with black holes playing a more active role in their development. However, these ideas are still in their infancy, and many scientists caution against overinterpretation. The key is to approach this discovery with both excitement and skepticism, recognizing that it opens new avenues of inquiry rather than providing definitive answers. Another aspect of the mystery is the technological and observational challenges involved in studying the early universe. Telescopes like the James Webb Space Telescope have allowed astronomers to peer further back in time than ever before, but even with these advanced instruments, the data is often limited by factors such as cosmic expansion and the faintness of distant objects. The black hole star in question was detected through its gravitational effects or the light emitted by its accretion disk, but these signals are faint and require sophisticated analysis to interpret. The team behind the discovery has emphasized the importance of cross-verifying their findings with other observational techniques, yet the process is far from straightforward. This highlights a broader challenge in astronomy, the difficulty of distinguishing between different phenomena when observing the universe at its earliest stages. For example, the light from a distant black hole might be confused with emissions from other astrophysical objects, making it hard to confirm its true nature. This uncertainty underscores the need for continued observation and refinement of theoretical models. Furthermore, the discovery raises questions about the role of cosmic inflation and the distribution of matter in the early universe. Inflation theory suggests that the universe expanded rapidly in the first fractions of a second after the Big Bang, leading to the formation of large-scale structures. However, the exact mechanisms that governed this expansion remain poorly understood. If early black holes formed under different conditions, it could imply that the distribution of matter and energy in the early universe was more varied than previously thought. This, in turn, could have implications for our understanding of dark energy and the universe's ultimate fate. Yet, these connections are speculative, and much more research is needed to establish them. The scientific community is now turning its focus toward addressing these unresolved questions. Researchers are working to refine their models of black hole formation, incorporating new data from observations like this one. They are also exploring alternative explanations for the discovery, such as the possibility of observational errors or misinterpretations of the data. At the same time, new telescopes and instruments are being developed to probe the early universe with greater precision, offering the potential to uncover more clues. For example, future missions like the Square Kilometre Array could provide insights into the distribution of matter and the behavior of black holes in the early cosmos. These efforts are part of a broader trend in astronomy toward interdisciplinary collaboration, where theoretical physicists, observational astronomers, and computational scientists work together to tackle complex problems. This collaborative approach is essential for making progress in a field as challenging as cosmology. However, even with these advancements, the road to understanding remains long. The discovery of this black hole star is a significant milestone, but it is just one piece of a much larger puzzle. As scientists continue to study the early universe, they will undoubtedly encounter new mysteries and challenges. Each discovery brings us closer to understanding the cosmos, but it also reveals how much we still have to learn. The journey of exploration is as much about the questions we ask as the answers we find, and this discovery is a testament to the enduring curiosity that drives scientific inquiry. In the end, the significance of this finding lies not in the answers it provides, but in the questions it raises. It reminds us that the universe is full of surprises, and that our quest to understand it is an ongoing adventure, one that is as much about wonder as it is about knowledge. Astronomers find black hole star in early universe. This part of our deep dive into Astronomers find black hole star in early universe focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Imagine a universe less than 1 billion years old, still glowing from the Big Bang, where galaxies are just beginning to take shape. Now picture a black hole, massive, hungry, and ancient, existing in this primordial era. This is the astonishing discovery astronomers have made, challenging everything we thought we knew about how black holes form and evolve. The findings suggest that a stellar mass black hole, roughly 100 times the Sun's weight, existed just 600 million years after the cosmos began. How is this possible? Because this black hole didn't form from a single massive star collapsing, as most black holes do. Instead, it seems to have grown rapidly, devouring gas and merging with other black holes in a way that defies current models. This discovery forces us to rethink the timeline of cosmic evolution. If such a black hole could form so early, maybe the seeds of supermassive black holes, those giants at the centers of galaxies, were already in motion far sooner than we imagined. But how did scientists spot this? They used the James Webb Space Telescope to peer into the distant universe, detecting the faint glow of a quasar powered by this black hole. The light took billions of years to reach us, meaning we're seeing the universe as it was in its infancy. This isn't just about one black hole, it's about the broader story of how structure forms in the cosmos. Theorists had long debated whether black holes could grow so quickly in the early universe. Some thought they needed a head start, perhaps from collisions between smaller black holes or mergers with gas clouds. This discovery supports the idea that black holes can accelerate their growth through intense accretion, even in the sparse, hot environment of the early universe. But there's more to it. The black hole's host galaxy also shows signs of rapid star formation, suggesting a symbiotic relationship between the two. Galaxies and their central black holes have always been linked, but this case hints at a tighter connection in the universe's youth. If galaxies and black holes co-evolved so early, it could explain how the first galaxies managed to form and stabilize so quickly. Yet, this discovery also raises new questions. How did such a massive black hole avoid disrupting its host galaxy? Why did it grow so fast without triggering the supernovae that usually mark the end of massive stars? These mysteries hint at unknown processes at play, perhaps involving dark matter or exotic physics in the early universe. The implications stretch beyond black holes. If the universe could form complex structures so quickly, maybe our understanding of cosmic timelines is off. Or perhaps the laws of physics themselves behaved differently in the first billion years. Scientists are now racing to model these scenarios, using simulations to test whether such a black hole could exist without violating known physics. Meanwhile, this discovery underscores the power of modern telescopes to peer into the universe's past. Instruments like the James Webb Space Telescope are not just observing distant galaxies, they're rewriting the story of how the cosmos unfolded. But this is just one piece of a larger puzzle. Astronomers have found other early black holes, but none as massive or as early as this one. Each new discovery adds another layer to the story of cosmic evolution, revealing a universe that was both chaotic and capable of forming extraordinary structures in its infancy. As we continue to look deeper, we're not just uncovering the past, we're reshaping our understanding of the present. If you've enjoyed this deep dive into the mysteries of the early universe, consider subscribing to FactVerse for more explorations of cosmic wonders. And if you have theories or questions about how black holes could form so early, share them in the comments. The universe is full of surprises, and every new discovery brings us closer to understanding our place in it.